Hey everyone, and welcome. Today we're going to crack open the digital vault that is Bitcoin. We're going to get right into the nuts and bolts, the ingenious engineering that lets a global financial system run without anyone in charge. No banks, no governments, nobody. And it all boils down to two core ideas: hash pointers and something called Merkle trees. Together, they create this incredible, unbreakable seal of digital trust.
So let's kick things off with a huge question. Think about it. In our world, digital stuff, files, photos, text, can be copied and deleted in a blink. So how on earth do you create a record, a history, that's permanent and completely tamper-proof? That was the puzzle Bitcoin had to solve.
And the solution starts with an idea that's almost ridiculously simple. Think of a line of dominoes. If you try to mess with just one domino, even one, somewhere in the middle of that chain, well, you know what happens. It sets off a massive chain reaction, knocking over everything that comes after it. That picture? Burn it into your brain, because it's the key to everything we're about to talk about.
All right, so how do we build this domino effect, but, digitally? Let's take a look at the actual links that connect each piece of history, each block, in this powerful chain.
It all begins with a tool called a cryptographic hash. The best way to think about it is like a super secure digital fingerprint for any piece of data you can imagine. You feed some data into this function, and out pops a totally unique code. But here's the magic. If you change anything in that original data, even just a single comma, that fingerprint changes completely. And, unpredictably, it's a whole new identity.
Okay, now let's build on that. The next piece of the puzzle is a hash pointer. It's clever. It does two things at once. First, it tells you where a piece of data is, like a regular link or pointer. But, and this is the important part, it also includes the cryptographic hash, that digital fingerprint of the data it's pointing to. So what does that mean? It means you can't just find the data. You can instantly verify if it's been messed with.
And this is literally where the blockchain gets its name. It's a chain of blocks. Each new block contains one of these special hash pointers, pointing right back to the block that came before it. This creates this incredibly strong chain where every single block is cryptographically sealed to the one before it, stretching all the way back to the very beginning.
And this is where the security really shines. It's just like our dominoes. If some attacker tries to go back and alter a transaction in an old block, the hash, the fingerprint of that block will change instantly. That creates a total mismatch with the pointer in the next block, which breaks that link. And that break cascades all the way down the line. The chain is broken. The tampering is just screamingly obvious to the entire network.
So the chain of blocks is solid, right? It's secure. But what about all the stuff packed inside each block? We're talking thousands of transactions. How do you efficiently create a single tamper-proof fingerprint for all of them combined?
The answer is it's a beautifully elegant data structure called a Merkle tree. And the process to build one sounds complicated, but it's really not. First, you hash every single transaction. Then you group those hashes into pairs, and you hash the pairs together. And you just keep doing that over and over until you're left with just one single hash at the very top.
Let's just build one right now. So we start at the bottom with all our individual transactions. In this little example, we've got T1 through T8. These are what we call the leaves of our tree.
Okay, step one. We run every single one of those transactions through our hash function. We're getting that unique digital fingerprint for each of them. So transaction T1 becomes the hash of T1, T2 becomes the hash of T2. You get the idea. We do that for every single transaction in the block.
Now we start building upwards. We take the hashes next to each other in pairs, smush them together, and then we hash that combined value. So the hash of T1 and the hash of T2 get joined together to create a totally new parent hash. And we just repeat that for all the pairs, right across the entire layer.
We just keep doing that. Pair them up, hash them, move up the tree, level by level, and eventually we're left with just one hash. One single hash sitting at the very top. This, my friends, is the Merkle root. It's the ultimate fingerprint that represents every single transaction below it.
Now, this structure isn't just about security, which is cool enough. It's also ridiculously efficient. Let's see how it lets you verify any transaction almost instantly.
So let's say your transaction is in a block that has, 4,000 other transactions. To prove that your transaction is really in there and that it hasn't been changed, do you have to download and check all 4,000 of them?
Thanks to the Merkle tree, the answer is a big, resounding no. So let's say you're Bob, and you just want to verify your transaction, T1. You don't need T2, T3, T4. You don't need any of the other transactions at all. You just need a couple of other key hashes.
And here's the absolutely brilliant part. All Bob needs are the sibling hashes on his path up to the root. So in this case, he needs the hash of T2, then the combined hash of T3 and T4, and the big combined hash of T5 through T8. With just those few pieces of data, he has everything he needs to rebuild his branch of the tree all the way to the top. And here's the moment of truth. If the Merkle root that Bob calculates all by himself matches the official Merkle root that's stored in the block's header, boom, match. His transaction is mathematically proven to be part of that block and proven to be completely untouched. It's just an incredibly efficient and powerful system.
The efficiency here is honestly staggering. What this fancy math really means is that as the number of transactions gets bigger, the proof you need barely grows at all. For a block with thousands of transactions, you might only need, say, 10 or 12 hashes to prove your transaction is in there. It's an unbelievably lightweight way to verify history.
But wait, there's more. This super elegant, really secure structure has another kind of surprising use. The Merkle tree isn't just for verifying things. It actually plays a huge role in the process of Bitcoin mining itself.
So the very first transaction in every single block is a special one. It's called the Coinbase transaction, and it's unique. For one, it doesn't spend existing coins. It actually creates brand new coins out of thin air as a reward for the miner. And crucially for our story, it contains this little data field called an extra nonce.
Right, so miners are basically in a race to find a valid hash for the entire block. They do this by changing a number in the block header, called a nonce, over and over and over again at incredible speeds. But here's the catch. There are only about 4 billion possible nonces. Once they've tried them all, they're stuck. They need to change something else in the block to get a fresh set of hashes to try.
And this is where that little extra nonce comes in to save the day. By making a tiny change to that extra nonce field in that very first transaction, the hash of that transaction changes. And because of the Merkle tree, that one little change cascades all the way up to the top, resulting in a completely new Merkle root. It's like shaking a snow globe. This new root gives the miner a fresh 4 billion nonces to test, and the search can continue.
Okay, so let's zoom all the way out now and just see how all these pieces, the hash-length chain of blocks and the Merkle tree of transactions, fit together to build a truly revolutionary idea.
So what's the big takeaway here? What does all this elegant engineering really give us? Well, this combination of hash pointers and Merkle trees gives us so much more than just a new kind of money. It gives us a system where history is practically set in stone, where verification is unbelievably efficient, and where the integrity of the whole system can be trusted without needing a bank or a government or any central authority. It's really a masterclass in how to build trust with pure mathematics. And that leaves us with a final thought. What other parts of our digital world could be rebuilt using this kind of trust?